Hello, so in this video, we're going to basically carry on from the last videos. If you remember the last videos, we were looking at this thing. So we were looking at the solution to the diffusion equation. Okay, so remember we came up with a model. This is the model which we came up with, or an equation which kind of modelled how an animal could move through time. Okay, and this was known as the Drift-Diffusion equation, sometimes known as the advection diffusion equation. Okay, but this is the Drift-Diffusion equation here. Okay, well, I basically consider the special case. If you consider the special case where you're not biased to move in one direction over another, so you're not more biased to move left, for example, than right, and vice versa, then therefore you're considering the case when L is equal to R, so left is equal to right. You're kind of moving in the same direction. That's basically the same case as we had with the simple random walk that we started with. Could either move left or right by equal amounts, and that basically then reduced this advection diffusion equation, drift diffusion equation, whatever you want to call it, down into what's known as just a diffusion equation. Okay, and this is a really famous equation in PDEs, actually, in partial differential equation. And in partial differential equation, we talk about sort of all different results of how to do it. But I mean, I did it in about a 40-minute video, I suppose a little bit longer, if you can sit in a couple of videos, basically just trying to do it by using this thing called the Dirac delta function. This Dirac delta function, okay? And basically I showed you that this actually was the solution to that. Okay, and we did it by basically using but we need initial conditions. So in other words, where do we start at? We need the information of where do we start at. And I managed to show you by using that, and we use something called the Dirac delta function. Remember, the Dirac delta function is just basically saying, well, at the start you will be at a certain position. Okay, so if you model the probability density function, the PDF, so in other words, how the probability changes over time. Okay, then basically over at the start, the probability of us being at the start position is going to be 1. So in other words, it's going to be an infinitely high peak, and that's known as the Dirac delta function. There's 0 everywhere else, and that's known as the Dirac delta function. Okay, so I basically showed you that in the last video. So basically now in this video, I'm going to try and use this. I'm going to try and use this to try and derive an equation, a solution to this kind of proper equation, the drift diffusion equation. So in other words, this is the equation with this term added. Okay, so that's what I'm going to try and do in this video. I'm going to try and use this solution here. Use this solution here to come up with a solution to this thing. To come up with a solution to this thing up here. Okay, so it's actually really straightforward. Basically, all I have to do is I have to take into account that I'm more likely to move over time. So I'm going to basically shift my distribution. If you imagine my distribution looks something like this over time. Okay, it looks something like this over time. So as I basically, the whole idea behind this is just a normal curve. Let me try and draw it out properly. Okay, so I've got a normal curve going on. Oops, normal curve going on. Okay, and the whole idea behind this is the position that I start with. This is the position I start with. So let's say I start at x equals 0. Then as time goes on, so as I move out through time, so this is probability on this axis. This is probability. As I move out through time, the probability of me being over here, probability of me being further away, probability of me being further away from my position point kind of gets less, because there's more options of where I can go to. It's a bit like if you start in the middle of a field. If you start in the middle of a field, so this is like a plan view of a field. Start in the middle of a field. Okay, well, as I move forward through time, there's more options of where I can go to. Because obviously I can be over here, or over here, or over here. So in other words, I'm getting bigger, so there's more options of where I can end up. So that's basically what this is saying here. So basically, by taking into account this term in the middle, so by taking into account of this term here, effectively what this is saying is that I'm more biased to move in one direction over another. So effectively what I'm just going to be doing is I'm going to be shifting. Let's see if I can do this. I'm not sure I can, but let's have a go anyway. I'm effectively just going to be shifting this distribution to the left or to the right each time. So hopefully you can see that. So effectively this drift term is basically saying that I'm going to be moving, my distribution, the centre of my distribution to the left or to the right each time. Okay, so that's all this drift term is effectively saying. That's all the drift term is effectively saying. So how am I going to move it? So effectively, I'm moving my distribution from x to x. So this x is just my position. So I'm moving it from 0 to where am I moving to? It's going to be u times t. This is basically saying, my new place that I end up is u. Okay, but it's going to change through time. Okay, so my u is going to change through time. It's not going to just be a constant place. Yeah, I'm not just going to end up in a constant place all the time. Yeah, it's constantly going to be moving. Let me try and show you this again. So it's constantly going to be moving to the left or to the right as I move through time. It's physically, this is, if you like, a real world, a real time kind of thing, if you know, a real time model. It's actually going to change through time. So therefore, it's not just going to be at one particular value. It's actually going to be dependent on time. So that's why there's a t in there. So basically, if I'm going to shift from x equals 0 to x equals ut, then I'm going to have to take into account of that. Well, I know that the solution to my diffusion equation is this. I know that the solution to my diffusion equation is this. So therefore, if I'm moving from x equals 0 to x equals mu t, then therefore I'm going to have to take into account of that shift. If you just remember from transformations of graphs, I'm effectively shifting x, yeah? Because I'm shifting x from 0 to mu t. So I'm shifting x from 0 to mu t. So if it's a shift, then therefore transformations of graphs just tells me that I'm going to have to stick a ut in here. Okay, and I'm just going to stick a minus in there because it's going to dictate a shift. It could equally be plus because I can move to the right or to the left. Okay, it's a bit like, you know, if I have a function, f of x, say, if I have a function f of x, okay, then if I shift it to the left or the right by, say, a, so I shift it to the left or right, say a, so let's say I shift it to the right by a, let's say I shift it to the right by a, then my new function will be f of x minus a. Yeah, I'm doing the, you know, say if it was x squared, then my new function would be x minus a all squared. That's exactly the same thing as I've got going on there, except I'm shifting it by ut now. So that's all this is. So actually, I can show you very easily that is actually, well, I'm not going to show you in this video, but you can verify that will actually satisfy this equation. That will satisfy this equation if you're that way inclined. Just use the same techniques as I was using in the last kind of couple of videos, and that will absolutely, you know, should absolutely satisfy it. But I know it will satisfy it because just by using that logic, that, you know, this minus ut in here, will just take into account of that shift in spatial distribution. Hopefully that makes sense. So now the last thing which I just want to do is I just want to show you how it changes over time. So over time, if I have a how kind of u and d kind of relate to each other. So if I have a small u and small d, so in other words a small shift and a small d, and a small diffusion, so it doesn't spread out that quickly, then therefore it's going to remain quite tight and close together. Whereas if I have a large, so this is small, okay, this is small, whereas if I have a large shift, so in other words I'm constantly changing direction and I'm changing it pretty quickly, then therefore I'm going to be more spread out. So I'm going to have a distribution that's spread out. So this is u and d, capital D, this is u and d large. So in other words, I'm more spread out. So basically, this would be like a prey species, perhaps, maybe, I don't know. That's perhaps, I don't actually, no, I'm not going to go down that route. But yeah, effectively, if I've got a small, I'm not moving about as much. That is what my u is telling me. So my u is telling me how I'm moving, whether I'm more inclined to move one way than the other, and my d is telling me how fast I'm doing that. So how fast I'm actually spreading out, how fast I'm moving. Okay, and so that's kind of the rough idea. So small u and d means that I'm kind of got a very tight spatial distribution, like this. Okay, whereas if I've got u and d being very, very large, I've got much more spread out. Okay, much more spread out.